Hello, everyone. Thanks for tuning in. I'm Suparna Sheshadri, and on behalf of OSA Student Chapter at Purdue, I'm happy to welcome you all to our webinar series. I would like to make a couple of announcements before introducing our today's speaker. As we had mentioned, we will be sharing the link to the Uber Eats lunch voucher 50 minutes down the talk in the chat box. So I request Purdue attendees to make use of that. Coming to today's speaker, we are delighted to virtually host Professor Marco Liscidini from University of Pavia. He also serves as technical advisor to Xanadu Quantum Technologies. His research is focused on theoretical study and modeling of light matter interaction in micro and nano structures. We thank Professor Liscidini to accept our invitation. I request everyone to post your questions during and after the talk in the chat box. And now I'll be happy to hand over to Professor Liscidini. Thank you.
Thanks a lot, Suparna, for the kind invitation. It's a real pleasure and an honor to talk even online. Hopefully soon I will visit Purdue University. And so today we're going to talk about generation of nonclassical light, linear and nonlinear photonic molecules. And if you want more information about my research, you can also visit my website here. And but let's start with the topic of today. Okay, so I will give you a brief introduction and about the basic elements you need to understand this talk. And then we will talk about these two structures in the context of parametric fluorescence. So linearly coupled resonators and linearly uncoupled resonators. So we'll see what do they mean and why they're useful. And I will give you some take-home message at the end and some perspectives about future work we are thinking about it. So first of all, for the people who are not familiar with the concept of parametric fluorescence is a kind of an umbrella for different spontaneous nonlinear phenomena. The most famous one is probably spontaneous parametric down conversion, also known as SPDC. So you can picture this like a spontaneous fission of a photon into daughter's photons. This is a second order nonlinear process, and it happens to be efficient in a class of material where the second order nonlinear response is particularly large. Now, second order nonlinear response is present in any material, in fact, but the dipole approximation, it is not present in centrosymmetric or amorphous material. So, for example, in silicon or glass, SPDC is very weak, almost undetectable, while there are other material like gallium arsenide, lithium niobate, and so on, in which spontaneous parametric down conversion is very efficient. We will see later what we mean very efficient, but efficient. And then there is another process, always in the context of parametric fluorescence, which is spontaneous Fourier mixing. And you can picture this process as the elastic scattering of two photons, which usually belong to a strong pump. And the process ends up with the generation of two daughter photons again, okay? So now here you can see I didn't choose the color random. So there is a specific energy constraint. So we have energy conservation in SPDC. So the daughter photons are have a smaller energy than the pump photon. While in the case of spontaneous Fourier mixing, since we are dealing with a full wave process, we have that one of the photons typically can have a larger energy, the blue one here, and the other one has smaller energy with respect to the energy of one of the pump photon. Okay, so also the direction of the arrows are not chosen randomly. So as you can see, I pretty much try to show you that this process must, of course, satisfy momentum conservation, which in nonlinear optics is typically known as phase matching. Okay, so this is an important requirement to observe these processes. Now, let's talk about numbers, because in theory, everything is usually quite easy, but in practice, we need to talk about numbers. And let's make this kind of mental experiment. We take a piece of silicon, 1 centimeter of silicon. We focus 1 milliwatt at 1550 nanometer, which correspond to a photon flux of about 10 to the 16 photon per second. And we focus it on an area of about 100 micrometers squared. And we try to understand, we try to calculate how many pairs we're going to see. Now, this is something we calculated a few years ago. The upper limit is a relatively simple expression. It depends on the nonlinear response of the system, which is basically the material, N2, and the area of focusing. And then basically depends quadratically on the pump and the length. Now, like this, you don't realize that if you plug in the number for silicon, you get 50 pairs per second. Okay, now before you abandon the talk, I tell you that we are going to make this more efficient, okay? And, but I want to even mention that silicon is a very strong nonlinear material. Other people prefer to use, for a number of reasons that will be clear later, a material like glass. In this case, since the nonlinear response of silica, for example, is an order of magnitude less than that of silicon, then you have, for the same power, 18 pairs per hour. Okay, so it's pretty clear that spontaneous forward mixing, and also SPDC, but spontaneous forward mixing in particular, is a very, very weak process. Now, it's useful to ask yourself, why is that? You may think that this is because spontaneous forward mixing is a quantum process. We are used to think that quantum processes are difficult to observe, elusive, but actually this is not the case. Spontaneous forward mixing is not weak because it's a quantum process, but it's weak because it's a nonlinear process, okay? And indeed, if you look at the formula I gave you here, now let's try to see the only number I didn't give you. I gave you the length, power, and everything, which is N2. N2, which describes the third order nonlinear response of silicon, is 10 to the minus 18 meters squared divided by 1. So it's a ridiculously small number, okay? So, but it's very important to understand that because since the problem is that this is a nonlinear phenomena, so obviously any strategy that helps to improve the efficiency of classical nonlinear phenomena can be useful to also improve the efficiency of spontaneous forward mixing. And this is what we're going to see as well. Now, imagine that you have this kind of very difficult event to observe, and we want to increase the light-matter interaction. Okay, what options do we have? So the first option, it's what I call the particle physicist approach. Okay, so in particle physics, there are some cases of events which are super difficult to observe. Among them, certainly, neutrinos events are very difficult to observe. Neutrinos are particles which are generated in many processes. In particular, there is a very intense flux of neutrinos from the sun. But neutrinos do not interact very likely with matter. And so neutrino events are difficult to observe. So one possibility is to observe a neutrino scattering with water, which result in Cherenkov radiation that can be detected optically, okay? But it's very difficult to observe. So what do particle physicists do? Well, they typically like big experiments. So I want to increase the interaction with matter. Well, I take a lot of matter. So that's their approach usually. So this is the Super Kamiokande experiment. So it's sitting in a mine in Japan. They have this huge pool full of water, and all of this are photodetector to detect Cherenkov radiation. And this is a boat with 2 people on it, just to show you the dimension of this experiment. Okay, so option 1 in our case may be going big. So one possibility is that, okay, let's just take a bigger crystal. Okay, now of course a lot of you are laughing right now, although I cannot hear you because you're mute. But actually this is not a stupid idea. And indeed, more than 10 years ago, people tried that by taking an optical fibers. In an optical fibers, what do? Well, you take a kind of a big system because you go from 1 centimeter, for example, to kilometers. And since this process efficiency is proportional to L squared, you can immediately realize that you can easily get between 6 and 8 orders of magnitude of enhancement, just because you go from a centimeter to kilometer, okay? So option going big is absolutely a possibility. But today we will focus on second option, which I called at least the elevator approach. So you want to increase the light-matter interaction, and light-matter interaction is very similar to people interaction. Okay, so imagine you have 2 people in an elevator, and you would like to see these people interact. Okay, so the probability of interaction is proportional to the time they spend in the elevator, and inversely proportional to the size of the elevator. Okay, so this is precisely what we are going to do with light and matter. So we need a kind of an elevator for light and matter. Okay, so we have a few options, at least the 2 options, at least 2, because you never know what people can figure out. And the first option are waveguides. Now here, notice that it seems similar to the previous, the fiber, but now here I'm not playing on the size of the elevator itself on the L. Here the size that I'm interested in is in the cross-section of the waveguide. And then I want to increase the interaction time. So I want to increase the time that light spends in the elevator by decreasing the groove velocity, by making light traveling slower, okay? And this is possible, for example, in an integrated device, or kind of integrated, in a photonic crystal waveguides. And this has been done. Spontaneous photonic mixing has been observed in more than 10 years ago in a silicon photonic crystal waveguide, thanks to slow light and a very tiny cross-section. But today we are going to focus on another class, which kind of looks like an elevator in a sense, like a box where you put light into, which are optical resonators. And here, the volume that we are interested in is indeed pretty much the volume of the resonator, while the time is proportional to an important feature of any resonator, which is the quality factor. It tells you basically the number of oscillation the electric field does before the energy is damped by a factor 1/E, approximately. Okay, so which kind of resonator we are looking for? So I made a little kind of a resonator wishing list, because not every resonator is okay for us. Of course, we want high quality factor resonator and small volume. This is for the same reason I mentioned you before. But then we also want a well-arranged resonances. What do I mean with that? Well, in nonlinear optics, especially in parametric fluorescence, we work with different kind of fields at different frequencies. So if we want to enhance the field at any frequency involved in the nonlinear interaction, we need more than one resonance. And this is actually usually tricky, because I need the resonances, and I need the resonances where I want. For example, if I consider single pump spontaneous photonic mixing, so when I have the generation of idler and signal photon by spontaneous photonic mixing, here I need 3 resonances, and you can see here they should be equally spaced. This to satisfy energy conservation. For example, if I deal with non-degenerate SPDC, well, in this case, you see, I don't need really equally spaced resonance. I need 3 resonances, and this must be located symmetrically with respect to half the frequency of the pump photon. So you see that in nonlinear optics, it's not just important having resonances, but having resonances well you want. And you will see that this is not always easy. Finally, third thing that I want is that I want a resonator I can actually fabricate. This seems kind of obvious, but you find in the literature many solutions which are absolutely unpractical. So you have to remember when you choose a solution that if you want to see an experiment before the end of your life, make it sure it can be fabricated. And then another important point, of course, you fabricate a device, but you have to be able to use it. And in this case, I mean couple light into and out. This is absolutely not guaranteed and not trivial. For example, in some photonic crystal cavities are extremely difficult to couple light into and out, although they have very high quality factors and may have the frequency range as you want. Okay, so don't give this for granted. So you put all these features, and then the winner is a micro-ring resonator. A micro-ring resonator is a spectacular system to do nonlinear optics. And how do you realize a micro-ring resonator? You take a rich waveguide with a certain cross-section, and then you fold it on itself, and you get a resonator. Okay, so this system has a natural comb of resonances, you can see here. So many resonances, this is what we want, many resonances. Then you can show that you can have a large field enhancement. This field enhancement in particular is proportional, is pretty much actually the square root of f. So there is, depending on the coupling condition, there is a factor pi in front of here, but pretty much is the finesse of this, is the square root of the finesse of the system. And finesse that can exceed 1,000 have been demonstrated in the system. It means that if you have a milliwatt in your bus waveguide, by the time you can accumulate up to a watt inside your resonator easily, okay? And notice that the finesse is defined like the free spectral range divided by gamma, which is the line width. This is very convenient because if you have a ring resonator and you take the spectrum, you can easily get information about the finesse and about the field enhancement inside the resonator. It's a very convenient measurement. And notice also that if you relate the finesse, the free spectral range, to the size of the resonator and the gamma to the Q, this is precisely what we were thinking about before. So the finesse tells you the amount of time that the light spends inside the resonator divided by the volume of in this case, the length, because the confinement, the resonant confinement is only along one direction, okay? So we have resonances, we have field enhancement. Another important thing is that it can be fabricated pretty in any material you can imagine. I don't think you can do it in cheese maybe, but probably people, we will think about it. You have silicon, silicon nitride, diamond, lithium niobate, gallium arsenide, gallium nitride, gallium nitride, polymers, pretty any material you want. Of course, with different results, but it's not rocket science. It's not like a photonic crystal structure, which is quite difficult to fabricate. Okay, so we have this system. Let's put it to work, and let's have some numbers now. Okay, so years ago, 10 years ago, here in Purdue, we made this experiment. We took a ring resonator, radius 5 micrometer, quality factor 8,000, so not a terrific quality factor, but at the time was okay. And then we tried to do this experiment, spontaneous flow mixing. So we pump 1 milliwatt of pump power here. Then the pump stays a while inside the resonator. And sometimes 2 photons of the pump are converted by spontaneous flow mixing and exit. And here you can see idler and signal. You can see that the pump is very intense, is about 1 milliwatt. And how many pairs? Let's see. So 1 milliwatt, exactly the same amount of power I mentioned you before with the example we started with. And you get 4 million of pairs per second, which is a lot because consider that I don't have a centimeter of silicon now. I have 30 microns of silicon. So the enhancement we're talking about is about 8 orders of magnitude. And there has been people doing even better than that. So with a resonator, you can easily get 8 orders of magnitude. Now, let's try to understand how you can get such a huge enhancement factor. Where does the enhancement come from? Now, if you calculate, if you write down the expression for the generation rate in the rate of generated pair in a resonator. Resonators are also nice for theoreticians because they're very easy to model. You can get an analytic expression for that. You have a formula which is very similar in a sense to the one I showed you before at the beginning. But you see there is a quality factor here. Not surprising, there is a resonator to the third power. Is inversely proportional to the radius square, okay? And then there is a gamma here. Now, the enhancement in a microresonator comes from 2 different cases. So in one, you have the transverse enhancement due to the field confinement inside the reach waveguide. So in general, the area is much smaller than what you can do focusing. Okay, so you have very tiny, almost diffraction limit area here, and this is an important enhancement. The other enhancement, the one which depends on the Q, of course, it comes from the finesse, what we have seen before. But where does this curious power relation come from? So it's about Q to the cube divided by V squared. So it's not just Q over V. So the Q counts a little bit more than the V, okay? Well, you can explain it very easily. So we have 4 fields involved because it's spontaneous full wave mixing. So each field, the field enhancement, in particular the intensity enhancement of each field is Q divided by V to the 4 because you have 4 fields. Then, remember the neutrino idea. So you have that the interaction is proportional to the amount of matter you have. And this square here remembers you that this is a coherent process. So this square is reminiscent on the fact that when you have phase matching, the generation rate comes from an interference effect, okay? And then finally, you have vacuum power. Why? Because this is a spontaneous process, and you can show that you can view a spontaneous process as stimulated by vacuum power fluctuations. Now, if you think about it, the energy of the generated pair can fluctuate within a line width. So the larger is the Q, the smaller is the vacuum power fluctuation. That's why you have Q divided by 3 and not Q to the 3 and not Q to the 4. Okay? So this works very well. Indeed, there has been many groups working in these more than a decade about spontaneous flow mixing in ring resonators. So we demonstrated here in Pavia a few years ago generation of entangled photon pairs, time energy entangled photon pairs. A lot of works come from a group in University of Bristol. This is actually a work from Purdue University, where the group of Andy Wiener who is here, and also the group of Morandotti in Montreal, where they use silicon nitride and here IDEX to generate frequency bin, entangled frequency bin using spontaneous flow mix. Okay, so in this introduction, we've seen the basic, and it seems like nonlinear optics with a single micro ring resonator is a walk in the park. You know, everything is easy, efficiency, you have, you can fabricate this ring and so on. But in fact, it's not exactly a walk in the park. So the people who managed to work with this system are very smart people, and doing this experiment is challenging, and also designing this system is challenging. Let's try to understand what are the challenges here. Okay, first of all, I admit I lied to you because I give you a set of equally spaced resonances. But in fact, in a ring resonator, this is not the case. In general, the resonances are not equally spaced simply because the effective index, the mode effective index, depends on frequency. So there is dispersion there. So if you want to arrange the resonances where you want, you need to do dispersion engineering. And how do you do dispersion engineering? Well, you change the cross-section of the waveguide, but typically you don't have any freedom in the world because in general, the height of the wafer is defined by the guy who's going to fabricate your ring. And the width, of course, you can change it, but there are limits provided by the lithography, but also provided by, for example, propagation losses that may increase if you decrease the width too much. So you have a certain freedom, of course, but not unlimited power, okay? Another important point to remember is that in a ring resonator, you have to remember that if you want to have a very high Q, you must satisfy this condition that the coherence length of your process must be longer than the length traveled by the light inside the resonator, which is Vg times the dwelling time of the photons inside the resonators. What does it mean? It means that the larger is the quality factor of your system, the more precise you have to be in arranging the resonances. Otherwise, you won't guarantee energy conservation, okay? And this is very important because we are now have the possibility to fabricate ring resonators even with quality factor exceeding 20 million in telecom. But of course, working with this system is kind of a nightmare with respect to the precision you need. Another important point is that you design your system, and then of course, you know that if you increase the pump power, you will increase your efficiency because this is nonlinear optics. So the efficiency is typically scaled with a certain power of the pump. But the problem is that when you have a lot of power circulating in your ring, you may have problems. For example, because of self-phase and cross-phase modulation, the position of your resonances will change depending on your pump. And this is a problem because it means that in general, you will be able to compensate for that by designing the proper dispersion, but this trick will work in a limited power range where the pump power and the dispersion will compensate with each other. The problem is that, again, the larger is the quality factor, the smaller will be this power range. And this is an issue, okay? Third, we said that it's a nice thing that resonators, ring resonators have many resonances because I need many resonances, but sometimes resonances are too many. For example, if I consider this process, dual pump spontaneous flow mixing, this is a situation where I use two pumps to generate identical photons within the central resonance, okay? Now, this is the process I want. I just want a pair of photons that are identical. Unfortunately, with this kind of arrangement, I have other processes which pollute my center frequency. And I don't want these processes. So this is single pump spontaneous wave mixing. We will generate a photon here and a photon here. Unfortunately, this photon here will be alone inside this resonator. And so it will pollute the state that I want to generate by dual pump spontaneous wave mixing. So in that case, you see, having so many resonances is a problem. Now, as I mentioned, all these issues sometimes, quite often indeed, can be solved by choosing a proper spectral range and by a careful dispersion engineering. But what are the options when you can't solve your issue with dispersion engineering? Okay, what are the options now? Okay, can we still use ring resonator? Of course we can. The first strategy is using linearly coupled resonator. And what's the philosophy here? Well, philosophy is that I have a ring which works very well with a set of resonances. And now I start to couple this ring to another one which shares some resonances. And anytime you have two systems which are coupled and they have the same resonant frequency, depending on the strength of your coupling, you have a rapid splitting and you have a splitting. So you have now the two resonances, which the coupling removes the degeneracy, and you shift and you control the position. Then I can add another one, for example, to tune another resonance. And so you can see the idea. Now, I can use linearly coupled resonator to create a kind of a photonic molecule, okay? Exactly like happens with energetic level in a molecule. This is a very interesting thing because it's a very powerful idea because depending on my needs, I can indeed arrange the resonances where I want. Let's try to see what happens in nonlinear optics. Now, here I have to give, so this is not work that I did. This is work by Milos Popovic's group, who worked very well as marvelous work given by Milos Popovic, who is also a very nice person. And he works a lot in linearly coupled resonators. And in particular, you see here, he took 3 identical ring resonator. So, and every resonance now is split in 3. And now here, the idea is that I want to observe nonlinear optics among these resonances, which now are the result of the coupling. So you see here, this resonance is a resonance which corresponds to light distributed on these 3 rings, the pump on these 2, and so on. So these resonators, these states are orthogonal, clearly orthogonal, okay, in energy, but also linearly orthogonal. But non-linearly, you can couple. And what they show was that you could do stimulated Fourier mixing, which means I can pump and see the one resonance and observe the generation of a photon pair, which result here in the generation of an anidler and here in the amplification of the signal seed. Now, just to mention that you can also play this trick not only with rings, although I was very, very bad on photonic crystal, but we actually worked in photonic crystal in the past. And again, here, it's very difficult to get many resonances in a photonic crystal. If you take this nanophotonic crystal, nanobeam photonic crystal, you have 1 resonance, but if you take 3 of them together, you can create, again, 3 resonances, likewise Milos Popovic's work. And what we did here was to study spontaneous wave mixing. And the advantage of using photonic crystal, although it's a nightmare fabricating this system, is that you can have a very, very efficient system. You can see here that the same generation rate in the photonic molecule is achieved with respect to the ring that I showed you before with 1/10 of the power. So it's very, very efficient. And the reason here is that the volume of the photonic crystal molecule, it's tiny compared to this system. Look, here is a micron, okay, and this is 5 microns. Okay, so the system is very tiny. Okay, so so far we have seen a situation in which I use a linearly coupled resonator to move the resonances that I need, okay? But now I want to show you another use of photonic molecule. This is more recent. So, and I'm talking about the generation of squeeze light via dual pump spontaneous Fourier mix. So dual pump spontaneous wave mixing, like I explained you before, this work is in collaboration with Xanadu, quantum technology. So I pump, again, through resonances of a ring resonator, and I want to generate squeeze light, okay? Exactly as before. But as before, I have an issue here. I have my single pump spontaneous wave mixing. So too many resonances, remember, okay? Not only the presence of these resonances, since I have to pump like hell because squeezing is very difficult to generate, introduces also the possibility of Bragg scattering for mixing. What does it mean? It means that because of Bragg scattering, which is a 4-resonance process, photons generated here can be up converted here or down converted here, or sometimes photons generated here by single pump spontaneous wave mixing can be up converted here, and so on. So essentially, I have unpaired photons in omega naught, and these reduce the amount of squeezing I can measure, because to measure squeeze, I need only pairs. In fact, it's like, if you think about it, you are adding photons, but the same effect is like having a beam splitter and losing a part of the photon, okay? Exactly the same effect. Now, obviously, the culprit here are these two resonances here that I would like to remove. So what do I do? Well, I had a resonator. And I split the resonances. So here, unlike the previous example, I use the resonator, the idea of molecule, to move, not to remove, because I cannot do that, but to move the resonances I don't want. Okay? So we call this structure a snowman, because it looks like a snowman, in fact. In real life, it looks a little bit less nice, but it's still this one. This is the picture of the nanophotonic molecule. We realize this is, I mean, nano, it's just because the waveguide is nanometer, but it's really an object which is micro. But, you know, if you call it nano, you know, it's fancy, okay? But it's certainly a microstructure. And what you see that if we calculate the spectrum, transmission spectrum here, because we chose the radius to be here 3/4 with respect to this one, you have here a resonance, here a resonance, here a resonance, and here a resonance of the head. And then you have here a resonance, here a resonance, and here a resonance of the body. And so you have a splitting here, okay? And then we are going to pump on this one for pump 1, on this pump for 1, 2, and then we generate on the central, okay? So all these 3 resonances, P2, S, and P1, belong just to the body of the snowman, while this auxiliary resonance, and then here and here, there are also resonances of the head, and so the splitting to remove the parasitic, the culprit, the resonances we don't want here, okay? So how does it work? It works very well, very well. So here is the squeezing measure without the suppression of the resonances. And you see that it's limited at 3 dB. And this is because essentially with no head tuned in the right position, you have basically 50% of the time the possibility to generate singlets inside the resonance where you are doing squeezing, which limits basically to 3 dB the maximum squeezing you can detect, while you can reach 8 dB squeezing if you are in resonance and when you have the head on and when you split the parasitic resonances and you suppress all these processes. So single pump spontaneous wave mixing and Bragg scattering for wave mixing. 8 dB internal squeezing is a lot, and it's still the record in an integrated device. And this work has been recently published, and you can go and look for the detail. So we talk about linearly coupled resonator. And now let's see the second part of the talk, as I mentioned, linearly uncoupled resonators. Linearly uncoupled resonators, interesting thing. So what's the linearly uncoupled? What are 2 linearly uncoupled resonators? Well, in one case is very easy. So this is the word, and here is in Lafayette, there is Purdue University. Here there's the University of Pavia close to Milan. And of course, I can have a linearly uncoupled resonator by taking a ring resonator in Purdue and a ring resonator in Pavia. So they're certainly linearly uncoupled. The problem is that you cannot do anything with those two rings. So what do I mean with linearly uncoupled resonator? Not just distant resonator, okay? So with linearly uncoupled resonators, I imagine to have a system like this. So I take a resonator with a set of resonances. Then I take another resonator with another set of resonances. And then here I put a coupler. But this coupler is actually designed to be an uncoupler. What does it mean? It means that if I take the coupling coefficient, which is nothing else than the overlap integral of the displacement associated with one mode here in resonator 1, and displacement with the other mode in resonator 2, no matter the resonant frequencies, I build this uncoupler such that this integral is 0. So this means that they are uncoupled. What does it mean? It means that if I imagine to have a tuner here, that can be an electro-optical modulator, for example, or a heater, okay? I turn it on, and the resonance of resonant number 2 will move, while resonator number 1 will stay still, because there is no field of resonator number 1 passing through the tuner. So they are linearly uncoupled, and yet they are close. Now, the tricky part now is also realize something which is linearly uncoupled, but non-linearly coupled. So here, if we take a directional coupler, I can choose the proper distance of the waveguide and the proper length such that light enters here and exit here, and so on. So these are linearly uncoupled, but you can calculate easily that the overlap integral, the nonlinear overlap integral of the fields belonging to the two resonator is different from 0. So they are non-linearly coupled. Namely, I can have energy transfer from 1 to 2 because of frequency conversion. Okay, and this has been proposed here, and recently we patented this idea of a linearly uncoupled resonator along with Xanadu. Now, I like to see ideas realized. So as soon as we have this idea, we try to fabricate a sample, and we try to prove non-linear coupling of linearly uncoupled resonator. And so we start at the beginning with something easier, which is stimulated forward mixing, okay? So we designed these two rings. You can see here, they're very similar to the sketch I drew you before. They're made of silicon nitride. This pump enters in this ring here above. It's very difficult to see the waveguide, but right here, while the seed is injected in this ring here, and the idler is generated in this ring, in this directional coupler, and exit from the ring below. So this is the transmission spectrum taken from different input-output channel. And the cross transmission is this one. You see there is a 20 dB cross transmission, and on resonance sometimes even smaller. So these are linearly uncoupled. I can using tuner, a thermal tuner here, I can choose the position of the resonances I want, and I can align them. So as I said, this resonance and this resonance belong to the bottom resonator. This one belongs to the upper resonator, and we see reasonable stimulated forward mixing here, which gives the generation of the idler. Very well. Now we see that it is possible to non-linearly couple, linearly uncoupled resonator. But what are, let's try to be more precise. What are the consequences of this? Okay, let's start with the bad news. The bad news is that the strength of the nonlinear interaction is clearly reduced. And there is a reason. Or better, there are two reasons. First, the nonlinear interaction occurs only in this uncoupler region, because it's the only place where field from resonator 1 and field from resonator 2 overlap. The second important point is that in general, this is something that we didn't prove, but in general, if you want to realize this kind of system, you have to work with the resonator with a larger mode volume. Not terrifically larger, but you see this, for example, is not a ring, it's a racetrack. And so you lose a little bit in finesse. So how much do you lose? So in general, depending on the design, we see that we can go from a penalty of about from 1 to 3 orders of magnitude. So this penalty can be relevant, okay? But can also be small. 1 order of magnitude, that's okay. You can, sometimes it's something you can tolerate, okay? But this depends a lot on the design. And we are discovering there are many, many ways to design linearly uncoupled resonators. Okay, so bad news. It's not that efficient as a ring resonator, but you know, a ring resonator is kind of a star in a linear optics. So it's okay, it's fine. Let's try to see the good news. Now, first important good news. Now, the design of bioresonances now is super flexible, okay? Much more than in a photonic molecule. Because I simply design a set of resonance here, a set of resonance there. I change the length here. I don't care about ratio between one resonator and the other. Completely independent sets of resonances. I can control the spectral position of the relative spectral position of the two sets. I can control independently the quality factor of this resonator and this one. This is very important, for example, to control quantum correlations. I can also control independently the coupling of the resonator to the external world, because I can, for example, critically couple this resonator and overcouple this resonator, for example. This is very difficult if you have a single resonator, okay? So this is an important bonus. Second important bonus. Now, the self-phase and cross-phase modulation can be compensated, and can be compensated without any dispersion engineering by design. Because you see, here there is a self-phase modulation depends, for example, if this is the pump ring, depends on the light circulating here, while cross-phase modulation here depend only on the pump, which is arriving in resonator number 2. So by design, I can imagine to compensate the effect and to change the ratio between self-phase and cross-phase modulation. And I can do it regardless the width of the reach. This is very powerful. Moreover, if I add a tuner, so if I have an active system, I can make the compensation properly active for any pump power. So I can increase the power range of my system because if I see that the effect of self-phase and cross-phase modulation increases, I can retune this one set of resonance with respect to the other to cancel this. And so I extend the power range in which the device can operate. Finally, dispersion engineering is no longer critical. And this is very important because sometimes dispersion engineering is a huge compromise because you need a certain dispersion, but playing with the width and the height of the ridge will have effect in the nonlinear parameter because gamma depends on the cross-section, and will have an effect also on the propagation loss because it will change the way the field sees the surface of my waveguide. And so, you know, sometimes you have a certain compromise, and sometimes you cannot even avoid with certain material combination to work with anomalous or normal dispersion and so on. Finally, interesting, the nonlinear effect is independent of the Q because the coherence length must be larger only of this length. So this means that once I know how to align the resonances, if this part of the system is space match, I will always have efficient spontaneous flow mixing no matter the quality factor. So it's totally Q independent. Okay, so we saw that this is possible in practice for a classical process like stimulated flow mixing. Okay, let's try to do it with dual pump spontaneous flow mixing. Okay, so we did it in collaboration with CLAT in a soy sample. So this is silicon, and we wanted to investigate spontaneous flow mixing, and we wanted to see that it was possible to eliminate parasitic processes in the dual pump spontaneous flow mixing. And this is easily done now because we literally remove the resonances because we are working with the nonlinear coupling of resonances belonging to different resonators. How effective is this in removing the parasitic processes is very effective, okay? This work was published 2 days ago, actually. And the signal to noise, so the number of pairs I generate over the single due to parasitic processes that we measure is 1,000. Actually, this is the floor noise. We didn't detect any spontaneous flow mixing process here, okay? So the signal to noise here is limited by our sensitivity, and it's 1,000, which is the largest signal to noise ever reported here, okay? Even more than the photonic molecule you saw before for the squeeze light. Okay, so we arrived at the time in which people that are sleeping because they are watching my talk on the coach should wake up at least for the take-home message. So you can miss the entire part of the talk before, but not this one. Okay, so let's give you 3 take-home messages. Okay, first, if you can do nonlinear optics with a single ring, do it. Okay, if there is no good reason, okay, use a single ring resonator. Okay, don't think about photonic crystal structure. Don't think about complicated system. If you can do it with a single ring, you do it with a single ring. There is no reason to complicate your life. But if you can't do that, you have two possibilities. So linearly coupled resonators, which are very useful to position the resonances where you need. Okay, for example, in the Popovich's work, or to move the resonances that you don't want. For example, in the photonic molecule, the snowman structure we have seen before. And this is linearly coupled resonator have an advantage here because they are relatively simple to engineer as well. But if you can pay a little price in efficiency and you really want to do something you can't do with a single ring or with the linearly coupled resonator, use linearly uncoupled resonator. It is possible. And effectively, you decouple the linear and nonlinear interaction. So you can optimize your linear properties, and then you can adjust the nonlinear interaction as you want. So you can optimize your waveguide cross-section to minimize losses and increase the gamma without caring about whether there is anomalous dispersion or normal dispersion or stuff like that. You don't need that because you can rearrange your resonances as you wish. So in particular, you have now a system that can be reconfigured, and this also can be reconfigured actively, increasing the power range of operation of your system, which is particularly interesting also in other applications like optical parametric oscillation, for example. And of course, this allows you to explore new configuration in a linear interaction. What do I mean with this? I kind of said it, but maybe it was not completely clear. So in a ring resonator, the gain in the parametric process, self-phase modulation and cross-phase modulation are linked together, especially if you work in a very narrow frequency range. Okay, the value of self-phase modulation, cross-phase modulation, and your parametric gain are kind of linked together. In this system, they are not. They're totally independent because the gamma depends on this uncoupler, the gain depends on this uncoupler, the self-phase modulation depends on the pump ring, and the cross-phase modulation depends again on the nonlinear coupler and this finesse and this finesse and so on. So you can imagine to work in a very different situation and also to explore, for example, optical parametric oscillation in, I don't know, normal dispersion or zero GVD, because you can do that and you can trigger these processes no matter your dispersion is, which is very interesting because people didn't think about it that much before, simply because in a single ring you cannot do that. So I finished with some perspectives. In particular, we can think about new uncouplers. This is something we are carrying on in collaboration with CLED. We talk about directional coupler, but this is not the only way you can do that. You can do a linearly uncoupled. This is a kind of a Mach-Zehnder ring. We call it Mach-Zing. And you can show that this system effectively results in linearly uncoupled resonators, and it works very well. And another things I didn't talk about because there was no time, so I had to make a choice. is that we are also working on second-order nonlinear interaction. You can do that. You can work with the linearly uncoupled resonator with second-order nonlinear interaction. It's all but trivial. We have already a work in progress in collaboration with Wolfram Pernis in Münster University, and part of the work has been presented to Clio, so if you look for the proceeding, you will find that. Let me finish. This is really the second last slide. We acknowledge an immense amount of people will help in reaching all these results that have been presented here at the University of Pavia, in particular Matteo Galli and Daniele Baioni, and also Federico Sabattoli. Xanadu, the people of Xanadu, in particular Blair Morrison, Zachary Vernon, Matteo Menotti, and Kang Tan. Then at University of Toronto, John Syke, with which I have a very long-standing collaboration, and in particular Corrado Shankalaper, because the sample we got from CLAT were exceptional, also thanks to his hard work. And thank you very much for your attention, and any of your question is very welcome.
Thank you, Professor. Thank you for the great talk. I would encourage everyone to ask questions. I could, since I don't see any in the chat box yet, I could start with one. Professor, could you please mention some thoughts, a few words on comparing the directional uncoupler that you talked about and the Mach-Zehnder uncoupler regarding how flexible you can have the resonance positions and their Q factors?
Okay, so this is a very good question in the sense that, directional coupler works well. It has the advantage that you have a compact system in the sense that clearly is easier, because in a Mach-Zehnder, as you have seen from the picture, you need at least two directional coupler to create the 50-50 beam splitter in general. So it's not that it's not a compact structure, so you have a larger penalty in finesse in the Mach-Zehnder. At the same time, what we have seen, and these are preliminary results, so I don't want to enter into details, but what we have seen is that the huge advantage of Mach-Zehnder is that the design is easier, and also the bandwidth is very large, because you can have a pretty large bandwidth, and our preliminary results show that you can have even a 100 nanometer bandwidth in which all the resonances are completely uncoupled. This is very tough for directional couplers, because you have to fight also with your fabrication capabilities, and so the minimum distance you can put the system and so on, dispersion a little bit, but not too much. But in general, the bandwidth of directional coupler is limited. But as I said, these are only two possibilities, but the concept is rather general. So I'm sure that there are other configurations that you can come up in which probably you don't even need nor a directional coupler nor a Mach-Zehnder. Okay.
Thank you.
Welcome.
Now, yeah, please, audience, please come up with questions. You can unmute.
Hi. Yeah, hi.
Hi, Professor.
Marco, this is Andy Weiner. Thanks for a
Yes.
wonderful talk.
Nice to see you, Andy.
Yeah. Well, so I was going to ask something related to Suparna's, but it came out about the directional coupler. But so I have a different, more basic one that's been puzzling me for a while. So if I look at the phase matching or the momentum matching conditions in a, let's say in a micro-ring resonator, some kind of four-way mixing interaction, is it simply K pump 1 plus K pump 2 equals K signal plus K idler? Or is there an additional possibility of 2 pi over the round trip distance, as sort of the extra, phase matching possibilities you would get with a grating?
So it's actually, no, you really need to do K1 plus K2 equal to K3 plus K4. And the reason is the following, because when you do the integral, this integral will be a sink of delta K times L. So of course, if you have delta K times L equal to a certain multiple of 2 pi, you will have a 0. But the problem is that since it's a sink, the denominator will go down like 1 over delta KL. So the point is that yes, if for example you have a difference of 2 pi, the penalty will be 2 pi squared. If you have a difference of 4 pi, the penalty will be 4 pi squared. So you realize immediately that this is a big penalty because 2 pi is 6, square is basically 36. So you really, it's through what you kind of suggested. You don't really need, you can work also with a finite delta k, but the problem is that since you go down like 1 over delta k L squared, this will go very, very fast down, okay? And this is a problem in a ring resonator because while here though, as you can see here in the slide, it's still on, the phase matching must be guaranteed only on this part. Why? Because anytime there is a round trip, there is a phase basically reset here. And so at the end of the day, the only phase difference, delta K, that you need is only this part. This is comes easily from the math. You can see it really from the math, but you can also imagine here. So there is a kind of reset because of the way it is a resonator, and so reset the phase. And this is very, very useful because clearly, I mean, the phase matching bandwidth operation of this thing is very big because it's just, you know, you need a coherence length of a few hundreds of micrometer, not a centimeter like in a situation where the quality factor is very large.
Okay, that's helpful, Marco. Thank you very much.
Welcome.
Okay. Anyone else has questions, please unmute yourself. I guess we already have shared the link to the voucher. If there are no other questions, then I would like...
I was trying to give the students a chance, but I'll ask one more.
Yeah. Yes.
So, Marco, another work I've seen in the literature, this is some work going on in the NIST Boulder group, for example, and sort of comb generation, you know, classical comb generation. Is another way sort of messing with the dispersion, if you will, is actually to sort of fabricate a grading structure, you know, within part of the waveguide, you know, some kind of Bragg grading structure. I'm just wondering if you have any perspectives or observations on that work. That struck me as kind of a very interesting idea as well.
Yes, I do, because so you're referring basically also to the work of Kartik Srinivasan.
Yes, sir.
Yeah. So yes, so you can play with it. So first of all, in Boulder, the advantage of Boulder is that when I mentioned that you have to be able to fabricate your ideas, I have to say that in Boulder the fabrication is so good that really they can fabricate stuff that is totally crazy. Because the grating they fabricated inside a ring and still having such a high quality factor is unbelievable. At the same time, so that example in particular, if I remember correctly, was about frequency conversion. In that case, frequency conversion, it's something where finesse is very important. And so when finesse is very important, linearly uncoupled resonator, you have a certain penalty in finesse. And so I'm not completely sure that this solution can be competitive, at least for the quality factor we have now. If we increase the quality factor like 20 million, 100 million, maybe one day, okay? I don't set any limit to quality factor anymore since because 20 years ago when I started doing linear optics, people said, oh, this is the largest quality factor you will ever see, and now we are a couple of orders of magnitude larger. So let's not set limits, okay? Now for OPO though, optical parametric oscillation, now the penalty of the finesse is way less because in the OPO threshold is basically proportional to Q square over V. So the fact you have a larger system like this one is not actually a big penalty. And you can, we calculated some OPO threshold with this system, and they are about 16 times larger than in a conventional ring. So it's not crazy. On the other hand, though, you can trigger OPO where you want. So if you can uncouple your resonators, you can basically go very far in region where normally you wouldn't be able to trigger your OPO because, for example, you cannot reach anomalous dispersion. While with this system, you can. And more importantly, when you start cranking up the pump power in OPO because you want a very efficient OPO, Well, you will have a very narrow operational range, while here you can retune the system and follow your pump and still being in the OPO regime. This is very interesting because we have seen many very low threshold OPO. There is this very nice work by Alfredo De Rossi, for example, in photonic crystal OPO. It's this fantastic work. They have a very tiny photonic crystal, very tiny threshold. But the problem is that also the output is very tiny. And if you try to increase the output, you miss the W resonant condition. And so you see, you have on the one hand a very low threshold OPO, at the end of the time, a very low output of the OPO, because if you try to pump more, it's done, okay? While here, you have a freedom in dynamic range with, I think, no dispersion can provide. Not even the grating, because the dispersion will stay the same while self-phase modulation will work. So it's something that you really have to follow, or you have to decouple, like I said before.
Good. Thanks again.
Welcome.
Thanks, professors, for the nice interaction. I would like to give a few seconds for anyone to come up with questions. Otherwise, okay, I'd like to thank Professor Liscidini for accepting the invitation, for giving this great talk, and